Can you turn on the mic? Good to go? Oops. All right. Hello, everyone, and welcome to the third press conference at the Division for Planetary Sciences meeting of the American Astronomical Society. I'm Shantanu Naidu. I'm the DPS press officer, and also helping out today are the AAS press officer, Rick Feinberg, who's behind, and also the AAS media fellow, Carey Lisse. Today we'll have members of the New Horizons team presenting the mission's January 1st flyby of the Kuiper Belt object, Ultima Thule. They'll cover the significance and challenges of the flyby, its science goals and operational timelines, and put the Kuiper Belt in context. Presenting first will be the mission's principal investigator, Alan Stern, from the Southwest Research Institute, followed by Carey Lisse from Johns Hopkins University Applied Physics Lab. And next will be Hal Weaver, also from Johns Hopkins University Applied Physics Lab. And finally, we'll have Kelsi Singer from the Southwest Research Institute. Before we begin the presentations, may I request everyone to turn your cell phones off. And we'll have the speakers present first, and after everyone's done presenting, we'll take question and answers from Q&A from you and people online. So, Alan?
See if this loads. Thank you, Shantanu, for getting us going. It says my presentation's launching. Okay, so it's launched just like our spacecraft. This is great, it's perfect. Yeah, well, thank you everybody for attending. We are super excited. You know, New Horizons has been, I think I speak for everybody on our team, and the tip of the iceberg is here. 2,500 men and women worked to build New Horizons and its launch vehicle, its nuclear power supply, and fly it across the solar system. It has been the scientific dream of a lifetime for all of us to be involved in it. And we're on to the next chapter, and that's what we want to tell you about today. I'm going to give a little bit of an overview, and then Casey and Hal and Kelsi are going to tell you a lot more about it, and then we'll answer your questions. So the next chapter for New Horizons, which has been crossing the Kuiper Belt now for over 3 years at very high speed, is the close flyby of a Kuiper Belt object named Ultima Thule. That's a nickname that was given to it as a result of a NASA-sponsored naming contest. And Ultima Thule comes from Latin, and it means beyond the farthest frontiers, which is exactly what we're doing. We're making the farthest exploration of worlds in the history of space exploration. The spacecraft is now about 1 billion miles farther out than Pluto, which itself was the farthest world ever explored. This cartoon that you see is a view of our solar system from beyond the Kuiper Belt, from a perch about 100 times as far away from the sun as the Earth orbits. Down in the middle of the diagram, you see the orbits of 4 planets in white ringing the sun. Those are the giant planets of our solar system. Earth's orbit is too scrunched down to see, and so would any of the other terrestrial planets. But the giant planets, Jupiter, Saturn, Uranus, and Neptune, can be seen here. Pluto's orbit is shown in amber. The spacecraft trajectory is in red. We launched this spacecraft on an Atlas V launch vehicle in January of 2006 on a direct descent trajectory to Jupiter. It was the fastest spacecraft ever launched, and at Jupiter received a gravity assist that sped it even faster to help us cross the solar system in record time. We intercepted the Pluto system in the summer of 2015, and then wrote a proposal to NASA for our first extended mission, which was accepted after senior review, and has a 5-year extent taking us out to 50 astronomical units, about the far edge of Pluto's orbit, but not at all the far edge of the Kuiper Belt. The exploration of Pluto that we conducted was scientifically spectacular. I don't think we could have expected any more from that binary planet and its system of 4 moons than what we found. And we're still working with that data, and there's a lot more to be done. Over 460 separate scientific observations of all 6 objects in the system by the 7 scientific instruments on board New Horizons. Well, in addition to being the first to explore the Pluto system, the New Horizons team and NASA are the first now to explore the Kuiper Belt. Ever since we left Pluto and fired our engines to divert to this trajectory to intercept Ultima, we have been using the telescopes, the radiation and dust sensors, the whole battery of instruments on board New Horizons to study the Kuiper Belt in a variety of ways. We're studying its environment, we're observing other Kuiper Belt objects that we pass in the distance, and now we're going to bear down on Ultima and fly by closer than we did to Pluto. That flyby is 10 weeks from yesterday, on January the 1st, 2019. I like to say spend your New Year's Eve with NASA and your Christmas in the Kuiper Belt. This is an artist's conception of what Ultima might look like to us, but really we have no idea what to expect. And I can tell you scientifically, that surprise and that discovery, whatever we find, is one of the greatest joys, I think, that you can have as a planetary scientist. Because we're going to an entirely new type of world, something formed much farther out than anything we have ever explored, and which has been kept in this tremendous deep freeze of the outer solar system for the entire 4 billion years since its formation. There's no other object that we've ever studied that has that combination of very great distance of formation and having never been warmed. All of the planets and the asteroids that we have sent spacecraft to have been much more processed thermally because they're closer to the sun. And even the comets, which formed very far out, some even perhaps at distances greater than Ultima, have been warmed by repeated passages to the sun, so that when we observe them, we think that they were pretty significantly evolved from their primordial state. Ultima is going to be something different altogether. Exactly what it will be, we can't tell you in detail. We know very little about it so far. We only discovered it in 2014 with a Hubble Space Telescope, working at the very limit of its fantastic capabilities. And we've been able to learn enough about its orbit to be able to intercept it and target it. But there's very little else we know. You'll hear a little bit more about it, but I have a model here in my hand of the comet that the ESA-NASA Rosetta mission orbited for 3 years, the ESA-NASA Rosetta mission. This comet is about 7 kilometers in scale and is very typical of the comets that we have sent other spacecraft to. I have a low-cost model of Ultima Thule to relative scale. This is a much larger object with about 1,000 times the volume and probably about 1,000 times the mass, about 10 times the linear dimension of Ultima, of these small comets. And really, we have never been to something like this that's so primordial, that formed on this scale. As I said earlier, it's the most distant and primitive object ever explored. As you cover our approach to Ultima and our fast flyby of it, be prepared for something quick. And although we're traveling at about the same speed past Ultima that we passed Pluto, Pluto is about the size of a continent like North America. And so when we were 10 weeks out from Pluto, we could already resolve its disk about as well as the Hubble Space Telescope. And each week, we could see more and more detail until we finally made the close approach. But Ultima, 10 weeks out, is just a dot in the distance. And it will remain as a dot in the distance until literally the day before the flyby, when we start to resolve it. And by the day after the flyby, we'll have high-resolution images. We hope even higher resolution than the best images of Pluto. So it's going to be quick. There's some danger and some suspense because we don't know in detail what the hazard environment might be. Our spacecraft is traveling 32,000 miles an hour. That's about 10 miles per second almost. And a collision with even the smallest shard would probably be fatal to the spacecraft. So as you'll hear a little bit later, we're conducting a hazard watch using the onboard telescopes and cameras, and we're prepared if we find rings or moons or other kinds of debris structures to divert from the closest approach that we plan to a little bit farther out where it may be safer. But we won't know until mid-December whether we have to take that course of action or not. And whatever we do, besides the scientific return, this is going to be historic. NASA was the first to the terrestrial planets, the first to the giant planets. Now it's first to the Kuiper Belt and setting a distance record for exploration that probably won't be broken for decades because no follow-up mission to go even farther is now planned. In addition, I want to be straight up that this is a tougher encounter than what we did at Pluto, and there are a number of reasons why. For one thing, we've only known about Ultima for 4 years, and so although the Hubble has let us refine its orbit, we don't know its precise position as well as we would like, and so we have to rely upon onboard optical navigation using the telescope camera system called LORRI on board, and then making engine firings to home in. And that is a challenging operation. There's no kidding you about that. Secondly, I just alluded to the fact that we don't know if there are moons or if there's a hazardous environment around this target. So we'll learn that primarily in December when we're starting to get close. But in addition, we're farther from the sun. So the lighting levels, which are already very dim at Pluto, are still dimmer. So our instruments have to strain more to collect good signal. And we're further from the Earth, which means the communication time to send commands to the spacecraft and to receive reports back is also much longer. At Pluto, it was a whopping 9-hour round-trip light time. For Ultima, it's a little north of 12 hours. So it just takes longer to take each step and to find out that it worked. And we have an older spacecraft, but fortunately still very healthy. We're not using any of the backup systems. But our power supply is a nuclear battery built by the Department of Energy. And it's fueled by plutonium, which, like all radioactive elements, has a half-life. And every year, it ticks down and doesn't produce as many watts. And so we have to manage the power on board the spacecraft to run all of its systems and the different scientific instruments very, very carefully. To just quote one number, the spacecraft power supply is currently producing 190 watts. That's about the equivalent of 3 standard US light bulbs to run everything on board the spacecraft, from guidance to command and control to communications to all the scientific instruments, all 7 of them, thermal control, everything. So we have to watch our power very carefully. And that combination of technical challenges will make this a much more daunting assignment to pull off flawlessly. So you're going to hear more about this from the next 3 speakers, starting with Kelsi. The new year is going to bring us some wonderful new knowledge from the edge of our solar system. We're going to set some new records, and we are really looking forward to bringing this to the public, to engage the public in what NASA does best, which is to explore. And there's one thing you can say about Ultima for sure. It's far out. Kelsi.
Thank you, Al. Next slide will work. Very good. So, good afternoon. I'm here today to talk about how Ultima Thule got where it is, and how we think it formed, and what we expect to see from the upcoming New Horizons flyby. Alan, I think, did a wonderful job of setting the stage. So I am going to talk to you with a bigger picture eyes. I'm going to take you outside the solar system and actually to think about the galaxy. Our story starts 4.6 billion years ago when our sun was forming. And it formed just like the other 100 billion stars in our galaxy. I'm going to try and use the pointer here, point to the left. And the process of star formation, as we understand it, It starts with a collapse from a giant molecular cloud. And that collapse forms a spinning disk surrounding a baby young star, a protostar, which you can see here left in this cartoon. And on all these cartoons I'm going to show you, below them I'm going to show you instances of real data. Here's an example of this HD100546, a nice fat disk that's forming a Jupiter with a star at the center that's occulted by that black disk, black coronagraph. But the point I want to make here is that as that star formation goes along, that disk continues to spin, things coagulate, collapse, you make asteroids and comets, and then you make planets. You make planets in the heart of the disk. But there's also material at the edge of the disk. There isn't enough to make giant planets or Earth-sized planets, but there's enough to make snowballs and dwarf planets and KBOs. And we think this happens in every single star system. So, and I'm going to hit this over and over again. And then as the disk matures and as those planets coagulate, they clean up, they take in all the mass, they grow to their full size, or stuff is thrown out of the solar system. You wind up eventually turning it into a mature system like the one we know today. I'll show you a better picture of this later. Or like the TRAPPIST-1 system everybody has heard about. Okay, so you don't have to believe me or believe those cartoons I just showed you. This is Hubble's view of 15 other systems. Every one of these beautiful rings, these beautiful disks, these beautiful images you're seeing, those are all somebody else's Kuiper Belts and planet-forming regions. And you're seeing the edge of those Kuiper Belts. They're there. Disks happen. Okay? So what I'm going to motivate over and over again, I'll say it now and I'll just say it again, is that we are going to our own edge of our own primordial disk. As Alan likes to put it, we're going to the third zone of the solar system that's never been explored before. So most people in the room know this. This is our solar system, wonder of things. Sun, and roughly to scale, the objects here roughly, the sun, of course, being at the center, and the planets in the middle, as I just mentioned. And at the very edge on the right, you see the Kuiper Belt. I want to point out that Pluto is in the inner edge or near the inner edge of the Kuiper Belt, that little yellow here. And then Ultima Thule is in the heart of our Kuiper Belt. And I'll wax metaphorical a little bit more, just because I was in the Explorers Club just a week or two ago, and I was seeing pictures and mementos from Admiral Peary's voyage to the North Pole. Every one of these planets has a North Pole. Admiral Peary was the first to our North Pole. Every solar system has a Kuiper Belt. We are the first right now with New Horizons to go to our systems, our planet's Kuiper Belt. This is quite the journey of exploration, just as Alan was saying. So what do we think happened in the Kuiper Belt? How did things form? How did they get there? What can we expect for Ultima Thule? Well, we think the KBOs likely formed, the very beginning of the solar system, that disk that I alluded to, is formed of tiny pieces of dust, thinner, smaller than your hair, on the order of a micron if you want a number, and molecules of gas. And over roughly about 1 million years, lots of collisions happen. Those pieces of dust aggregate into particles that are the size of BBs and marbles. You can see them in the smaller pieces here. And that takes a long time. But once they're about BB and marble size, through a process that we're now calling pebble accretion, you see much, much more rapid collapse into larger kilometer-sized bodies, with the occasional impact happening too, as we're motivating in the picture here on the right. So what does pebble accretion create? Well, we think, from the best models we have today, that it creates bilobe or bilobate. We discussed which term to use on the team, but it creates elongated and bifurcated structures. They could be anything from binaries, just two bodies orbiting each other, to contact binaries that have a neck, like some of the comets we've flown by in previous missions, or even an elongated potato-like structure. Cucumber, whatever, pick your favorite vegetable. But the point is that we think it could create any one of these structures. And because if you work out how long it takes for binary KBOs to interact with each other in this very edge zone where there isn't too much material, they can interact with each other. They can possibly collide about a few times in the history of the solar system. So about once or twice every gig year, every billion years. That means that if we formed these structures early on, they very likely can survive. Impacts don't happen very often. The impact velocities are relatively low. So we have a good chance to see a bilobate or extended structure. And lo and behold, when we went to Argentina in June and July 2017, we found, by looking at the pattern of the shadow that fell on the Earth as this body went by a star, a background star, we saw a pattern that definitely, as you can see on the left, that definitely showed us a bilobate structure. There are two different parts to this body, or an extended body. So we are seeing something that's definitely not spherical and something that's going to be very interesting. And as Alan already alluded to again, this could very well have the seeds of its formations still there because it formed, possibly had a little bit of evolution. I'll talk about that in the next slide. But then it has been in deep freeze and the edge of the solar system just waiting for us to go find it. So I talked about where it is. I've talked about what shape we can expect it. What do we think we're going to find on the surface? Over that same 4.6 billion years that this body has been out in the Kuiper Belt, these snowballs have been burnt by cosmic rays, by the solar wind and high energy solar radiation. So we expect that their surface could or most likely very dark. And when I'm showing you these images, I know you're captivated. These are 4 solar system objects they're real objects, so I'm going to talk about their structures and textures and what we can expect. But these have all, I want you to remember when you're looking at them, they look kind of bright to your eye, but they've all been extremely stretched. These are all bodies that are as dark or darker than coal. They are black. If you actually were out there looking at them with your eye, yes, they'd be slightly brighter than black deep space, but they're dark. And they're dark because they have been burnt. Not exactly the same way you burn stuff in your kitchen, but burnt with high energy radiation, burned with cosmic rays, burned with X-rays. However, we're still in a region where it's very cold. So that after possibly a little bit of radioactive heating, a little bit of activity when they first formed and coalesced into these multi-kilometer sized bodies, they have settled down and they're most likely been inert. And that means if they've been cratered, they've been hit by something, as you can see on some of these bodies. Again, I'm going to go through the bodies in detail. Then it's possible that crater never healed, unlike what we see on a comet when we come to a comet that's close into the sun. It never melted, never boiled away and just kind of healed over or removed the scar, if you will. So we can possibly expect lots of craters. We can also expect, as I'm going to point here, this is VILD-2, the Stardust mission target. These are multiple pits. We think they're actually sublimation pits. Material has evaporated and then collapsed. The remnant material has collapsed behind it. So think of them as sinkholes, if you like. This body has lots and lots of them, but it was also been very close to the sun. Ultima Thule hasn't been. On the other hand, it could have had aluminum-26 radioactive heating early on in its life, which could have meant there was a very early epoch of a bit of activity and possibly some sinkholes. And again, because this body never got close to the sun, the sinkholes never healed. They happened, they stayed. If you look at the moon of Phoebe here, we think Phoebe has done both. It's less sinkhole, if you will, than VILD-2. VILD-2 shows very few craters. Phoebe shows more crater holes. The object here, Hyperion, in the middle here, or to the middle right, is actually been incredibly, it's almost like a sponge. It's been incredibly evaporated and dissipated. And let's see if I need to do this one more. Nope, it's already done. As you'll notice on the surface of Phoebe, we've painted a bright spot. This bright spot is what we might expect if a collision happens. You don't just get a crater like you see over here on Phoebe and the crater darkens up after time. It's possible that this crater could punch through the very thin, what we think, cosmic ray burnt layer and actually dig down into primordial ices that are much, much brighter. We don't know. But if we do see something like this, we'll be absolutely thrilled, pardon me. And on the right, everybody knows this is one of the beautiful images of comet 67P Gerasimenko. And this object has been incredibly thermally processed. We don't think that we're going to see this for Ultima Thule, but we might get surprised. So these are all textures, if you will. You see craters, you see sinkholes, you see craters, you see possible, here's a bilobate structure, you see also a neck, you see maybe some thermal alteration. We could possibly see any or all of these, or maybe none. What I want to point out is that what we know today about Ultima Thule, the darkish 15 by 15 by 27 kilometer object that we've probed with Hubble and with the occultations, seems to fit the story I've given you. An object that formed in the Kuiper Belt has remained there their entire life, seems to be roughly extended or bilobate. Looks like its albedo is about 10%, which is what you kind of expect. It's a little brighter than the cometary ones I'm telling you about, but it's not bad for the moons I'm showing you in these images. But if New Horizons Flyby has taught us anything, and Alan has again already pointed this, expectations aren't reality, and that's why we explore. We got totally surprised at Pluto. We're going to get surprised again, and that's actually the fun of it. I can say one thing as a member of the team, probably one of the best moments I've had scientifically, well, one of the best, and one I've certainly had on the team, was when Alan woke us all up and got us up at 5:30 in the morning, was it at APL? And he showed us the brand new absolute first image of Pluto, high res, ever seen by mankind. And after the first wow, within, I'd say about what, a minute, we all started up and started poking at things and saying, oh, that's the mountains, oh, that's a flow. And we're going to do that again. We're going to get up there and we're going to just jump on Ultima Thule. And that eureka moment, that exploration moment, is one of the things I live for scientifically. So thank you. And I'm looking forward to doing that again. So I've motivated again. I'll just say it and finalize. UT could be heavily cratered, highly pitted, or it could even be smooth from ancient flows and ancient activity. We don't know. And as I said, it could be totally unexpected. We simply aren't going to know until we get there in January. And I'm waiting to be surprised. Okay, and so I sent you a big picture. I'm going to hand it over to Hal and Kelsi, who are going to tell us about the details, how we're going to go from this big picture to actually making these measurements, and how we're going to figure out how it formed and how it got to be where it is. Thank you.
Okay, thank you, and thanks for coming. Well, as you've heard, we know very little about Ultima Thule, but that's about to change. And the reason that's going to change is because NASA's New Horizons spacecraft has a suite of highly advanced scientific instruments that we're going to be using to explore Ultima Thule. And just as some background, I want to just give you a quick tour of the spacecraft and the instruments. This is an artist's conception of the spacecraft, artist's drawing of the spacecraft to the left there. It's roughly 7 feet across, and we like to say that it's about the size of a baby grand piano, weighs about as much too. But let's go through the instruments, which are, we have arrows pointing to the various instruments. So we'll start with Ralph, which is on the far right side of the spacecraft. Ralph is really 2 instruments in one. It has a highly capable color camera and an infrared spectral imager, and it's mainly used to probe the composition of the surface. Right above that is the Alice ultraviolet spectral imager, and it'll also probe the surface, but in addition, it'll be searching for activity, potential cometary-like activity near Ultima Thule. And then as you go around the spacecraft towards the middle there where you see LORRI, those are the eagle eyes of this spacecraft. The highest resolution camera that we'll be using to explore the surface in the greatest detail. The big radio dish there is how we collect the radio signals that are used by the REX instrument, the radio experiment, that we can use to measure the temperature of the surface of Ultima Thule. And then we have a couple of instruments that measure particles, several instruments. Highly charged particles from the sun coming up from the solar wind, emanating from the solar wind, and ultimately impinging on the surface of Ultima Thule. Those will be monitored by the SWAP instrument. And then the PEPSI instrument will be searching for highly energetic ions in the vicinity of Ultima Thule. And then finally, underneath the spacecraft, you can't really see it here, is a student dust counter, a student experiment that is looking for little dust impacts as we fly through the solar system, and in particular as we fly by Ultima Thule. So that's the suite of instruments that we could be using to explore Ultima Thule. And in fact, we've already started. We've already detected Ultima Thule with the LORRI camera. In fact, about a month earlier than what we originally thought. But it wasn't easy. If you look at the image to the left, those are a bunch of stars in the background. Surrounding Ultima Thule is at the crosshairs there. But in that left-hand image, you really can't pick out Ultima Thule. You have to subtract away the stars, which is what we did on the right-hand side, and then you see Ultima Thule popping out. And we see it very clearly. So now Ultima Thule is in our sights, and as we get closer and closer, it'll get brighter and brighter, and we'll be able to gather more and more information about it. But as we've heard, we're going into the unknown, but we're not flying blind. We are already seeing Ultima Thule with the LORRI instrument, And we're going to do careful systematic observations all the way from now through the flyby. We'll be monitoring the brightness variations of Ultima Thule, that'll inform us about the size, the shape, and its rotational properties. We'll be searching for any potential moons around Ultima Thule, and also looking for debris, dust, that could be in the vicinity that could potentially be dangerous for the spacecraft. And of course, we use that camera to hone in on the aim point that the spacecraft is headed for as we fly by just about 2,000 miles, 2,170 miles above the surface of Ultima Thule. But we will have an opportunity, if we do see something that concerns us, something that looks dangerous, we do have the opportunity in mid-December, after looking carefully at the data, to divert the trajectory, to change the trajectory away. Instead of going quite so close, we go a little bit farther away, still have a fantastic mission, but avoid damage to the spacecraft. And that decision will be made in mid-December. Let me just give you a timeline now, a simplified timeline for the Ultima Thule flyby. This starts in June to the far left and goes all the way through March on the far right in 2019. Let's start from the top. Throughout this entire period, we'll be doing observations with our particle instruments, the plasma, the SWAP, Pepsi, and then the student dust counter. All throughout this period, there'll be several opportunities, 5 different opportunities for us to use those navigation data to decide whether or not to fire the thrusters on the spacecraft to divert the trajectory to head us to exactly where we want it to go. And then in late November and early December, we'll be making very intensive observations of the environment around Ultima Thule, looking for satellites, potential moons, or dust that could potentially prove harmful to the spacecraft, and make a decision on December the 16th about whether or not to fly the currently planned trajectory or to divert. You can see that the star there in the middle of the yellow portion of the timeline, that's where we are today. So as Alan said, just a couple of months out from the flyby. And we're taking data throughout this entire period. The yellow means that the spacecraft has been put into a special mode. It's no longer spinning, which is what the purple meant. We're now able to command the spacecraft in 3-axis, what we call 3-axis mode, to point wherever we want, and we'll be pointing at Ultima Thule, but we'll also be doing lots of other distant Kuiper Belt objects, observations with the LORRI instrument, because we're in the middle of the Kuiper Belt. This is a once-in-a-lifetime opportunity, literally. And we're going to observe a couple of dozen other Kuiper Belt objects as we fly through the Kuiper Belt. You'll see that the closest approach is on New Year's Day. Let me show you in a little bit more detail in the next slide, right around the time of closest approach. On December the 31st, we'll have a couple of downlinks of data. Everything is fixed on the spacecraft. The antenna is fixed, so we can't send data back down while we're trying to observe. So instead of sending data back to the Earth, we actually point everything at Ultima Thule and make observations so we can optimize the scientific return. But we will turn back a couple of times. And on December the 31st, we'll have some images that will give us they'll whet our appetite for more. We'll see, the latest images that we'll get before the closest approach will be similar to what Hubble sees of Pluto right now, roughly 5 pixels across, something like that. So it'll be enticing, but wait until afterwards. That's when the real rich data set is going to come down. We will have a spacecraft, what we call a phone home, on January the 1st, a very short pass with the Deep Space Network, just some engineering data to make sure that the spacecraft is fine, and then look for a really rich data set with some of the best images, the best spectra, all of the best data coming down during January the 2nd, January the 3rd. Just to whet your appetite a little bit, imagine you're on the New Horizons spacecraft flying over New York City, looking down with the LORRI camera at Manhattan Island, okay? On the left-hand side, that's the resolution equivalent to what we get during the Pluto flyby, okay? You know, roughly 8,700 miles above the surface, looking down. And you know how spectacular the results were from the Pluto flyby. But if you look to the right, that's the kind of resolution that we expect to see as we fly even closer to Ultima Thule. And you can see it's like putting the glasses on and everything coming into focus, just amazing resolution. And that's what we expect to see just a couple of days after the new year. And so with that, I'd like to turn it over to Kelsi, and she'll tell you about the scientific objectives and give you a sense of what kinds of data we'll be sending down.
Thanks, Al. Hello. I think you guys have all got the theme that we don't know what we're going to find there. But whether we find features that we've never seen before or we find some more familiar features, we're of course going to map those. And we'll also have the right kind of data to be able to do get topographic measurements, so the heights or the depths of the features. And we'll look at the color and the composition, just like we did for Pluto. And here's an example of one of Pluto's small moons. And as a couple of my colleagues have already talked about, this will be our first ground truth, if you will, but our first close look at what makes these objects dark and red. And a lot of other objects out where where Ultima is have this same characteristic. And so that'll be really important for us understanding these objects. We'll find out if there's one main body or multiple main bodies. And of course, Hal already talked about looking for satellites and rings for hazards, but also just to learn about that, and it'll tell us about how the system of Ultima Thule formed. And we'll also be looking for a coma-like feature, which could be made out of gas or could be made out of something more like grains of dust or ice. This is a simulated image using Saturn's moon Phoebe. And this is what our highest resolution LORRI will be, so that's black and white. And we also, because we're flying so quickly through past Ultima, we'll have some smear. And so all of that has been simulated here. And so it gives you a pretty good idea of the kinds of detail we'll be able to see. And you can even see some little albedo changes here across the surface. So if things like that are present, we will see them. This is a simulation of our best color. It's a little bit lower resolution, as you can see. And here we've modeled it as reddish because we know it will be reddish. But this is an example using Mars's moon Phobos. And again, it gives you an example of the types of color resolution we'll have. Looking for satellites and rings, of course, we don't know yet if any of those are there. But these are, again, what would be an example of what could be seen in LORRI as we're approaching. And the picture on the right is just what kind of processing we might be able to do in order to pull out really faint features like the kind of ring thing you see around here. This would be the very bright Ultima in the middle. All right, so what are we going to get back in the early downlink periods that Hal mentioned? So on December 30th, late in the evening, we will get a picture with more than 1 pixel. And so that will have been taken earlier. This is when it arrives to us on the ground. And it's 10 kilometers per pixel, and Ultima is about 30 kilometers probably at the longest, so that's why we get 2 to 3 pixels across there. And then by the next day, we will have doubled our pixels. And so you can see it gets a lot better after that as well. So these will be downlinks before closest approach, and then after closest approach, we'll get the higher resolution stuff that you see on the right. So in the evening of January 1st, we'll get about 100 pixels across, and then again, twice as good as that the next day on January 2nd. And you can really start to see the shape and details that we'll be able to see. We're, of course, getting back a host of other kinds of data. Hal already talked about the instruments and what they do. So this is not all the data we're taking. This is just the stuff we're able to get back early. So we'll have some color, some composition that comes from our spectral instrument. We'll have data looking for that search for a coma feature, either from the gas. And then we'll also have a REX scan of the dark or unilluminated side of Ultima that will give us some temperature data. And then we'll have dust and particle and plasma instruments to tell us about the environment around Ultima. And with that, I would like to invite you to come along with us for this journey. And in particular, since this is a press event, you can see down at the lower right here, there's a link to register to come to the Flyby and get information about what's going on then. Thank you.
Thank you to the presenters. We'll take Q&A now. Please raise the mic. Carey will bring you the microphone and introduce yourself before asking the question.
Yeah, I'm Alex Witzy with Nature, and I know you don't know what you're going to see, but I want to ask if some or all of you will speculate on a little bit about what you learned from Pluto and how that might inform what you're thinking about. I guess I'm mostly interested in the fact that there was so much active geology on Pluto, even though it was in deep freeze. And I know you talked about melting and kind of making more active geology, but can you talk a bit more about what you learned from Pluto and how that may or may not inform whether or not you might see cool active geology here as well?
Who wants to take a crack at that?
I can try if you want. Well, there's some similarities and differences. The first thing I think of is that we learned at Pluto the reason why it has such a high albedo, why it's so shiny and bright, is because it has a lot of ice on its surface. And we've actually now gone and used that to go think that some of the other large Kuiper Belt objects that are high albedo could also have possibly atmospheres and hazes and surface ices. We're not seeing a very high albedo for MU69 for Ultima Thule. It's only about 10% or so. So most likely it doesn't have that, it's not doing what Pluto was doing in terms of ice and atmosphere. It's most likely is darker. On the other hand, it's not the 4% albedo that we typically see for cometary nuclei. It's not totally dark. There's something going on that's making it twice as bright as your average comet nucleus. So that story, or the idea, or the model I pointed out that just totally burnt surface, 4.5 billion years old, just sitting there, something seems to have made it brighter than we would nominally expect. So could that be a big crater? Could it be that it does have some activity? We don't know.
So I'd like to add that because Pluto's a really sizable object, its internal geophysical engine has created a whole host of geological and atmospheric and climate processes that we don't expect to see on an object this small. It may have had some activity very early after its formation because of the radioactive decay of elements from the original solar nebula that were incorporated into it and that bottled up some heat and may have driven some early activity. If we find recent activity in an object this small, that would be very large point headlines. Yes. Because we would not understand how that happened. Obviously, we're going to be on the lookout for that, but it's not expected. One of the things that I'm looking to find out is how this object accreted, how it formed. The going paradigm, the model that was in place for decades for the formation of small objects was that they were built up through the collisions of still smaller objects that added mass and added mass and added mass in a process called binary accretion or hierarchical accretion. In the last 10 years or a little more, about since the time that we launched, there's a new theory for how many of these objects may have formed, which is called pebble accretion. And pebble accretion has some different implications. You might expect a more uniform uniform surface rather than something with lots of subunits in it that came together as different objects. But in addition, in pebble accretion models that are being shown as research results at this very meeting, it's oftentimes the case that when formation completes, there are a large number of what are called pebbles, but they can be much larger objects than just pebbles. They can be football-sized and boulder-sized and even moonlet-sized objects that could be orbiting Ultima in a swarm, very close to its surface. And we have never seen anything like that. New Horizons is going to have the capability to in the space of 1 week, the first week of January 2019, confirm or refute the very models that are being presented at the Division of Planetary Sciences meeting. And I think that's going to be amazing.
Nola Red, freelance. Just as a follow-up, they were also talking about gravitational instability as a possible formation mechanism today. David Nesmorny, and I'm wondering if you would comment on that one. What you might see if that was the case.
Well, there are a variety of different forms of gravitational collapse models, but most of them would again predict a more uniform type of structure than a binary accretion model. So we're going to be looking for clues in the surface geology, and Kelsi's our geologist here at the table. And we're also going to be looking for clues to the formation mode by what's orbiting around Ultima within its gravitational sphere of influence. And if it's clean as a whistle and nothing's there, that's important evidence that'll take the theorists in one direction. And if there are rings or satellites, that's a kind of information. And if there's a debris swarm left over from accretion, that's still another pathway.
And Nola, just to add to that, you can have a gravitational streaming instability that builds a somewhat large object on a few kilometers, and then the pebble accretion can come in and complete the body. So you can actually have a two-step process. They don't necessarily compete, if you will. They can actually work in tandem.
Luca?
Hi, Luca Maltagliati from Nature Astronomy. So there was an occultation last August of the object. Any update that you can mention?
Mm-hmm. So I can give you a general report. We predicted that Ultima would create this occultation. That's when the target passes in front of a star and makes it wink out. And by putting telescopes in the shadow, we can refine the orbital position of the target, and we can trace its silhouette, its shape, whatever that might be. This particular event was very difficult because the majority of the occultation path was across the Atlantic Ocean. And at the edges in South America and in North Africa were the only landfall that was there. We deployed teams with multiple telescopes to Colombia and to Senegal. The Senegal team, unfortunately, was completely weathered out. It was completely cloudy on the night
Colombia.
of the...
You mean
I meant to say, excuse me, Colombia. Completely weathered out. They didn't get any data. In Senegal, it was also very cloudy, but there were some breaks in the clouds. And it looks like at least one, and possibly as many as 3 of the 24 telescopes saw Ultima make the star wink out. And Mark Bowie is going to be reporting on those results in a couple days. That has helped us refine the orbit considerably, but with only 1 for sure and up to 3 traces, the results are ambiguous. Fortunately, in 10 weeks, the problem is going to solve itself. And you know, this has long been a mission of delayed gratification, and I'm sorry to tell you, hang on for 10 more weeks. We'll see.
Do we have online?
Yes, we have a question online from Daniel Fischer. He's reporting for Adventure Astronomy and Sky Week in Germany. His question is for Kelsi. He says, can't the smear around closest approach be corrected by image processing, Wiener filtering or something like that? Amateur astronomers, after all, have successfully de-smeared some Cassini close-ups of Saturnian moons.
Yeah, great question. And the simulated image that we showed actually did take some of that into account. And there is some reconstruction that you can do, but it's still not quite the same as if you didn't have the smear to begin with. But there are we have fortunately very expert image processors on our team as well. And I've also seen amateurs do a lot of really great work. And so those images will be available for people to play with and improve as they can.
But just to emphasize, rest assured, we actually have the expertise to do the de-smearing and deconvolution to pull out the maximum information that's available in all these images. So tell Daniel we're on it.
Okay, I have a couple of questions myself. Rick Feinberg, AAS press officer. when you passed Pluto, you turned the spacecraft around and did a solar occultation so that you could look at the atmosphere. Now, I know Ultima Thule doesn't have an atmosphere, but are you doing anything on the way out, looking back at all? And if so, what are you looking for?
That's a great question, Rick. There are a number of experiments we're doing. And although, as you said, we don't expect to find an atmosphere around this object, it's hard to imagine how it could still be outgassing after 4 billion years. We're going to look. And we're doing something similar to an occultation called a solar apulse, which means we'll watch the path of the sun, and we'll also watch stars traverse through where its atmosphere will be. It won't get down onto the hard deck and actually occult the object, but it will pass through where the atmosphere would be. And we'll look for signatures of atmospheric absorption with the ultraviolet spectrometer. In addition, the cameras on board are going to be looking back at this favorable geometry that allows us to detect minute amounts of dust or debris that could be orbiting with or orbiting around Ultima in rings or other kinds of dust structures.
Forward scattering?
Forward scattering is the right term. And we're also going to be looking at the surface of Ultima because in that same geometry, because that will teach us about the properties of the surface, how fluffy it is, how dense it is, how reflective it is, that add to our knowledge on approach by looking at this forward scattering geometry. Those are the two primary experiments as we leave, but as you heard a little bit earlier, we're also going to be using our radio science instrument to measure the night side temperature, which compared with the day side temperature can tell us about the thermal conductivity of the surface, which is an important parameter to understand Kuiper Belt objects. Our plasma sensors and dust sensors will be measuring the environment on that side, the far side of the object. So we're going to be applying all of the instruments to the best of the instrumentation capability during the first day and a half after the closest approach. But Ultima will be rapidly receding because of our speed, and it will eventually drop below the detection capability of all the instruments within just a couple of days.
I want to add just a little bit to Alan's excellent answer. Just two small points, if you will, seasoning or flavoring. One is that we wouldn't have detected the haze of Pluto. We couldn't detect it when coming and looking away from the sun. We had to turn around and look back. So and if you want to get a sense for that, just a human kind of sense for that, when you're driving near sunset and you suddenly see all that dust and all the dirt on your windshield, it's not because it's suddenly gotten dirtier. It's because that's forward scattering. It's enhanced the amount of your ability to see that dust. And that's the same kind of effect that we're going to use.
Sorry, I have one more questions come in online, so let's do that one. This is from Bill Harwood at CBS News down in Florida. How long will it take for the entire Ultima Thule data set to get back to Earth after the flyby, given the great distance and the data rates and the solar conjunction?
So we transmit the data back with a 30-watt transmitter, not 30 kilowatts like local radio station, 30 watts and over 4 billion miles. Despite that, NASA's Deep Space Tracking Network can maintain the link and allow us to transmit at rates of a little better than 1,000 bits per second. But we're collecting about 50 gigabits of data. And we can't communicate with the Earth all the time because we share the Deep Space Network with the whole fleet of NASA interplanetary spacecraft. So when you put all that together in a computer and you model, it turns out that very much like it took 16 months to get everything back from Pluto, it took us from July of 2015 until October of 2016. This is going to take a little bit longer because we're farther away and the bit rates are lower. It should take us about 20 months, give or take. So data will be coming down all of 2019 and most of 2020 into approximately August, September, at which time we should have all of it on the ground.
So just to add to that, can't keep doing this, but I'm trying to help.
Keep at it.
30 watts is much less than the power in one of these lights that's illuminating us right now. And for those of you who are old enough in the room to remember dial-up, 1 kilobit per second is, remember when you watch pictures row by row by row show up on your computer screen? That's what we're getting. That's what we've got.
But you weren't dialing up from 4 billion miles away.
No.
Thank you. Jay Pasikoff, textbook author. Now that I learned from Alan about the looking back mode and how important it is to get those observations, first of all, if it's the far side, it'll be dark, so can you really see structure on the surface? But second, you do have to rotate the spacecraft, of course, because NASA didn't give you enough money in the first place. So there will be a hiatus in the data taking looking back in order to send back some images. So how is your schedule going to work between those two things?
Hal showed you the initial downlink schedule. And we send back 3 sets of high priority data on January 1st, 2nd, and 3rd. The first of those arrives on the very late afternoon of January 1st, and we're planning a press event on January 2nd to show off those first images. Kelsi showed you some simulated versions of what they might look like using objects that have already been explored by NASA spacecraft. The observations that we make on departure only take about a day and a half. So that, compared to the 20 months to get all the data back, that's not much of a delay. And while we're there, that's a very important time for us to make observations that you could never make, no matter how big a telescope you ever built on Earth. If you can imagine in Star Trek century, having telescopes that could see the geology on a Kuiper Belt object, it still can't see the far side because it's pointed the other way. So this is a very unique opportunity to do that science. As we departed Pluto, we looked back not just at the planet Pluto in its atmosphere, which you're familiar with those like blue ring images of Pluto's atmosphere, but we also looked back at its satellites, like Charon, and saw just a sunlit crescent at this high phase angle geometry. And that's been used in the same way that I described we will for Ultima, to study the scattering properties, the fluffiness, the reflectivity, the porosity of the surface. So we already know that the cameras on board can do this.
So that's the crescent.
Right.
And so how long is in hours, will you take out of your data taking in order to transmit these high priority first images?
Just a few hours. We have, I think, a 4 or 5 hour DSN pass on the first day, a little bit longer pass on the second and third days.
One last question, Nola?
I'm just curious, in terms of Ultima rotating, do we know how much it's going to rotate while New Horizons can see it?
We wish we did.
Okay.
One of our team members had a program on the Hubble Space Telescope to measure exactly that in the summer of 2017. But the result was inconclusive. Probably, we think, because the pole direction of Ultima is probably pointed towards the Earth. So no matter how it turned, it presented the same face to us. We'll find out if that interpretation is correct, but we don't know its rotational period. If we did, we could plan some aspects of the flyby better. So as I said, we're flying into the unknown with a very capable spacecraft, and it's going to be all about exploration.
And stay tuned, because we're systematically observing it from now as we come in and seeing some changes in the geometry that might start to give us some information on the rotational properties. But as Alan said, so far, it's been flat.
And we'd actually like it to rotate, right? Because then we can see more of the illuminated surface. But we're not, as Alan's pointed out, we haven't seen any evidence that it's rotating significantly.
Sure, if it's a quick one.
I'm just curious about the New Horizons orientation in respect to Earth.
Clarify your question, please.
Okay, like you were talking about the Ultima rotating pointed towards Earth. Is New Horizons still like not rotating, but moving so that its north is the same as Earth's, or has it changed over the time? So
I'll say a little about that, and maybe Hal Weaver can add to it. So our spacecraft uses control jets to point itself to any position that we command it to, or to track moving targets, like Ultima, or any satellites it may have. During the flyby, it'll position itself many times in many different ways. In fact, currently, it primarily either points to put the antenna back to the Earth so we can communicate, or to put the cameras on Ultima, which is approximately the opposite direction in the sky. When we fly by Ultima, if you'll let my fist maybe represent Ultima. We're going to fly, we don't know where its pole is, but we're going to fly to the direction of celestial north, sky north, over the top at one of these two distances that Hal described earlier. 3,500 kilometers is the nominal, 10,000 kilometers is the backup to the celestial north. And during that entire time, as we're approaching, going through closest approach, and then departing, the spacecraft is pointing many times in order to adjust for the changing viewing geometry on the target.
So let's end it there. Thank you, everyone, for the presentations and for being here. We'll have one last press conference tomorrow. That will be the Hayabusa 2 space mission press conference. And hope to see you tomorrow.
Thank you.
Thank you.